Okay, so let's look at this problem. Astronomical observations of our Milky Way galaxy indicate that it has a mass of 800 billion solar masses, 8 times 10 to the 11. A star orbiting on the galaxy's periphery is about 60,000 light years from its center. What should the orbital period of the star be? Okay, so now, so let me draw the Milky Way galaxy is a spiral galaxy, and here's a top view of the galaxy. So what is being said is a star in the periphery, and the radius, orbital radius of this star is 6 times, r is 6 times 10 to the power 4 light years. Okay, and they're asking you what should its period be. Okay. All right, now as the star goes around at a velocity v, the centripetal force is provided by the gravitational force, and all these stars within the orbital radius contribute to gravity, and which is 800 billion stars. Okay, so let's put all this together. So mv square by r is equal to g mass of the galaxy times the mass of the star divided by r squared. And the mass of all these stars act as if it's a point mass as long as it's within the orbital radius. Okay, so the mass of the star cancels, one of the r's cancel, and the orbital velocity is square root of gm, the mass of the galaxy, divided by r. And what should the orbital period be? So the period velocity is the time taken, 2 pi r divided by the period. Okay, so the period is 2 pi r divided by velocity. So let's add a page. Okay, so the period is 2 pi r divided by velocity, and we're going to substitute the expression for the velocity we got. 2 pi r divided by square root of g mass of the galaxy divided by r. Okay, so I suppose we should have calculated the velocity. Yeah, no, it's okay. Okay, so the square root of r goes to the top, so it's 2 pi r to the power 1 plus half, that's 3 halves, divided by square root of gmg. Alright, now let's put in the numbers. 2 pi r to the power 3 halves. Okay, 1 light year, by the way, is the distance traveled by light in 1 year. So 1 light year is equal to, here's the speed of light, meters per second, and each year has 365 days, 24 hours, 3,600 seconds. Okay, so that's 1 light year. And okay, so let's calculate this value. 3 into 365 to 24 36 367 10 to the power 15. Okay, so 9. So, and a light year works out to, so 367 9.46 1. Okay, I'm going to just write okay, 1 light year equal to 9.46 into 10 to the power 15 meters. That's what that works out to. Okay, so R is that okay, so the period is 2 pi, R is 60, 6 times 10 to the power 4 light years, and each light year is 9.46 into 10 to the power 15 meters. Okay. And this to raised to the power 3 halves, and G 6.67 times 10 minus 11 Newton meter square kg square. And the mass of the galaxy. The galaxy has 8 times 10 to the power 11 solar masses, suns, and the mass of each sun is 3 times. Okay, the mass of the sun. Let me look up the mass of the sun. Two times 10 to the 30 kgs. So that's how many suns, 800 billion suns, and each sun, the mass of each sun is 2 times 10 to the 30 kgs. And this whole thing to the power half, square root of that. Alright, this is messy, so let's calculate this. Okay, let's take care of the powers of 10. So this is 2 pi 10 to the 4, 10 to the 19 we'll make that 10 to the, this is 10 to the 4 plus, that's 10 to the 19. We'll keep 18 of that. We'll spend a 10 there, so 60 times that, 10 to the 18, half of that is 9, and 9 times 3 is 27. Okay, so 2 pi times 60 into 9.46 in the numerator to the power 3 halves times 10 to the 27. And in the denominator, let's look at the powers of 10. It's 10 to the 11, that kills that, and 10 to the 30, and square root of that is 10 to the 7, 10 to the 15. So 10 to the 15. And I'm assuming all the units will work out. We've kept everything in SI units, so, and it's square root of 6.67 times 8. Okay, so this period should work out in seconds. Okay, so this is equal to, and okay, so let's do the This is 10 to the power 12. 27 minus 15 is 12, so 10 to the power 12 seconds. And let's figure out this numerical value, the prefix. Okay, 60 times 9.46. This is to the power 1.5 into 2 into pi. Okay, divided by okay, so 11,632 times 10 to the 12 seconds. So 1.16 times 2424, so 10 to the 16 seconds. Okay, so that's the orbital period of the star. That's how long it takes to go around the galaxy once. Okay, now we will calculate this in years and see if this number makes sense. Okay, so the period is 1.16 times 10 to the 16 seconds, and 1 year, so we'll convert this to years. Year is 365 days, 24 hours, 3,600 seconds. Okay, so 1.16 367.8 million years. And this is roughly, this is the right order of magnitude. And the reason I know that is the orbital period of the sun. The orbital period of the sun is about 200 million years, and the sun is not quite at the edge. So this is roughly about the right order of magnitude. 3.6, yep, okay. Now let's see, what does part B say? If the period is 60 million years instead, what is the mass of the galaxies? So what they're saying is, instead of 368 million, 367 million, it's 60 million, so 1/6 the period. And let's see, so let's go look at the period formula. So here's the period formula. The period is, we're going to keep the orbital radius the same. So if the period is smaller, that means there must be more mass than we see. And so since the period is 1/6, this denominator is, well, this is, so the mass is 36 times greater than what we see, because square root of 36 would be 6, and that would give you a 1/6 the period. Oh, wow, that's crazy. So the mass would be, so you see right from this formula, if the period is 1/6, the amount of matter should be 36 times greater. That is absolutely crazy. Well, it turns out that dark matter, the unseen matter that we talk about, is about 5 times the normal matter in the universe. Okay, so let's calculate what should the new mass be. Okay, we need to add a page below. All right, so we'll call it. Okay, here's how we'll call it. So T is 2 pi times r to the power 3/2 square root of gmg. So that's the expression. And if t prime, the period, the new period, the actual period corresponds to mg prime. Okay, so t divided by t prime should equal 2 pi r to the power 3/2 square root of gmg divided by 2 pi r 3/2 gmg prime. Okay, everything cancels, but so here's what you get. So t, and you can check this, t prime is square root of mg prime divided by mg. So if for this period, that would be the mass of the galaxy. For this period, that should be the mass of the galaxy. Okay, so what does the problem say? So the problem says if the period is 60 million years instead, what is the mass of the galaxy? All right, so we got, for our calculation, we got 367.8 million years. And we want to calculate what would be the period for 60 million years. Okay, which would be mg, and what I'll do is I'll calculate it in terms of the old mass, so which would be more sensible. So the thing on the left hand side is years 367.8 divided by 60, 6.13 equal to mg prime mg. Okay, and so mg prime is square of that, it's 37.6 times mg. So it's roughly 40 times the mass that we can see. Okay, so the theory is either there's a massive black hole whose mass we can't see, well, we could feel its mass, but or there's other forms of dark matter. Okay, and that's quite a bit of dark matter. And does that end the problem? Yeah. So anyway, since we mentioned dark matter, let's state how much dark matter there is. Okay, so if this were here the pie chart, content of the universe, contents of the universe. Okay, so oops. 70% is dark energy, and 5% is normal matter, and roughly 20% is dark matter. Okay, that ends this problem.